Thank you, Magnus, and thank you, Anu, for that wonderful introduction. I'm delighted to be presenting the Bodhi lecture today, and good day, everyone. Let me share my screen. And let's go to full view. So title of my talk is Climate Change Mitigation and Adaptation, Role for Systems and Controls. Before I plunge into the talk, I have put a lot of background material as hyperlinks in this presentation. I'm going to make the PDF of my talk available on my website, so you can go in there and look up all the content that I'm drawing on in my talk. As I think about this Bodhi lecture, my mind goes back to 1989, when I was a junior faculty member growing up in the profession. And Gunter Stein from Honeywell gave the inaugural Bodhi lecture, which was electrifying, to say the least. There is a wonderful article in Control Systems magazine on Gunter's talk, along with a very nice paragraph by Carl Ostrom, which I highly recommend reading. So I give this talk with respects to Gunter Stein and everybody else who followed him in the tradition of these Bodhi lectures. So our story begins with this chart, which is a depiction of global greenhouse gas emissions since 1970. Now, we could have gone back further, but it really doesn't matter. As you can see, the key greenhouse gases are carbon dioxide, land use change, methane, nitrous oxide, and fluorinated gases. And pretty much it's a chart of rising GHGs since 1970. And we have more or less doubled just in that period total GHG emissions on an annual basis. Now you can see a slight dip in 2020 because of COVID-19, but it's fully expected that 2021 will see a big rebound. And so this curve will continue to go up. So what's the impact? Well, here are some charts that show the impact. So temperature, global average temperature, since the start of industrial age has gone up by 1.1 degrees Celsius. These are taken from the latest IPCC report. And as you can see, this warming is unprecedented in the last 2,000 years. This is the actual observed temperature, and this is where the 1.1 comes from. And this second chart on the right-hand side shows that this is really caused by human and natural system interactions. As a result of this rising temperature, several things are happening. And on this, there is increasing consensus in the research community. First of all, hot extremes are rising. So this is again a chart taken from IPCC. What it shows is it divides the globe, Earth, into zones. And for various zones, it asks the question, is there increased occurrence of hot extremes? And as you can see, pretty much all over the world, with few exceptions, there is strong consensus and high confidence that hot extremes are increasing. And in the US, certainly we saw that in Washington, state of Washington, in California, and many other parts of the nation where temperatures increased. Almost nowhere do you see a decrease. So hot extremes are increasing. Second big thing that's happening is heavy rainfalls and flooding. So heavy precipitation. And again, you can see in a lot of places around the earth, there is increased precipitation and flooding as caused by this greenhouse effect. And again, the level of confidence is not as high as in case of hot extremes, but it's still significant in many parts of the world. And the third thing that's happening is droughts. So not only are we having flooding and rainfall, we are also having droughts in many parts of the world. And again, you can see, for example, Western North America, there is medium confidence that global warming is causing ecological and agricultural droughts. You can see similar effects in Africa, in many parts of Europe and Asia, and so forth. In addition to these effects on hot extremes and flooding and rainfall, as well as droughts, there are projections that if temperatures keep increasing, 3 billion people will be living in areas where the average temperature will be 29 degrees Celsius, which is really, really hard. And you can see much of that is in Latin America, in Africa, in India, and so on and so forth. In addition to these hot conditions, there is sea level rise and impact on coastal populations and flooding, human and animal health impacts of hot extremes, wildfires and flooding, ocean acidification, which will have huge impact on marine life and its impacts, climate change driven migration. As many areas of the world become unlivable or difficult, people will move, and it is projected that hundreds of millions of people could be moving from where they have been to different areas where they can possibly live. So that's going to cause massive changes, and jobs, work, economic and societal disruptions are likely. Now, I'm not going to speak about many of these things. I'm going to concentrate on just a subset of these impacts. Okay, so this has already happened and is happening. What lies ahead? Now, what lies ahead is that global population will continue to increase, sort of mostly in Africa and some in Asia. And economic activity will continue to increase. So this is the chart taken from IEA. World's population expands to 9.7 billion people, and global economy is more than double as large as 2020. So if the economy continues to grow, and that has its own implications, as I will show momentarily, this is what is likely to happen. In view of all this, people have been discussing for the last, I don't know, 30 years or more, how we might bring all this situation under control and not have the extreme effects of climate change. And this goes under various scenarios. Of course, this is all about the future, so we really don't know what the future holds, but we can think about what the future holds, just as I showed you, that the economy doubles. And can we achieve that doubling while also controlling the global warming? So these are different scenarios. On the left-hand side are different, so Paris Agreement target that I'll talk about in a second, and a band around 1.5 to 2 degrees Celsius global warming, and different emission scenarios. And so in very low emission scenario, we can stay within 1.5 degrees. And in low emissions, we can say between 1.5 and 2. But then as you go into higher levels of emissions, our temperature increase gets worse and worse. Now, to achieve these low emission scenarios, there are different models for how socioeconomic conditions will evolve over time, over the next 20, 30, 40 years. And there are different illustrations of various models where global CO2 emissions as well as non-CO2 emissions, particularly methane. Methane is high impact global warming gas, and that needs to be brought into control in the coming years. And then there's black carbon, nitrous oxide. Well, you know, like if you are like me, who've been watching the news out of Glasgow and COP26, you're probably disappointed, as I am. And here is a chart that kind of beautifully captures where we have been. So it goes back to Paris Agreement in 2015. It brings Glasgow, which just finished, and then what happens beyond. So this is the trajectory that we have been on, and this is really where we need to go. The pledges and targets that we have as of Glasgow are somewhere in this region. And in September 20, which was before Glasgow, the gap between where we need to be in 2030 versus where the Paris Agreement left us was roughly 23 to 27 gigatons of CO2 equivalent. And that has been shaved down a little after, so this is the November 21 update after Glasgow. So sum total of all this is that it is believed that we are on track for roughly 2.5 degrees Celsius global warming, and certainly not within the 1.5 to 2 degrees Celsius that we aspire to be in. That's sort of the background. What I'm going to do now is focus down into the energy sector, which is the single largest sector behind global warming. And I want to begin with a key observation, that the energy system is gigantic, literally gigantic. It's multi-scale. It's distributed, it's dynamic and interconnected. So let's begin with energy consumption. And again, you can see from 1970, our consumption of oil, coal, natural gas has just gone up pretty much monotonically. Coal is coming down in recent years, but other fossil fuels keep increasing. And then there is some increase in bioenergy. And you can see wind and solar also in this sort of bottom part of the chart. I'm going to talk a lot about wind and solar in the coming minutes, but just to show you, even in the last 10 years, where wind and solar have seen spectacular growth, because our total energy consumption keeps going, the net share of fossil fuels from between 09 and 19 over one decade has decreased only by 0.1%. Okay. Now we have had, modern renewables have grown from 8.7 to 11.2%, in part driven by wind and solar. And so you might ask, where has the decrease been? And it's probably largely been in sort of use of nuclear and other sources of electric power. But the main point I want to make here is that our use of fossil fuels in energy consumption has really not decreased by much in the last decade. Just to think about US, and so that you get an idea about how the energy system works and how complicated it is, this is a beautiful diagram called the energy Sankey diagram from Lawrence Livermore National Labs. On the left-hand side are the primary sources of energy. So petroleum, biomass, coal, natural gas, and so on and so forth. They go through various transformations, electricity generation, for example, but sometimes they're used directly, like say natural gas is used in industrial processes or in our residential heating and appliances or in commercial uses. And then you have petroleum that drives a lot of the transportation system and some of the industrial system. So you can now chart, how primary energy gets used in various end uses. And ultimately, of the 100.2 quads of primary energy, and one quad is 1.055 times 10 to the power 18. The reason I like it is because it captures the US energy consumption in a very simple number, 100. Okay, so US consumes 100 quads of primary energy, of which only 32 quads essentially are useful services. Rest is rejected energy. So we end up wasting a lot of primary energy. Now, some of it is inevitable because of laws of thermodynamics, but a lot of it is because we are not efficient users of energy. Bottom line of all this is that major energy transitions are very slow. And this is a point made eloquently by one of the leading thinkers in the energy space, Václav Smil. And he makes the following observations. He says that let's look at a primary source of energy, say coal, and ask the question, in 60 years, after it became 5% of global energy consumption, what was its penetration in 60 years? So coal starts at 5% in 1840, and in 60 years, it goes to 50%, okay? Oil became 5% of global energy consumption in 1915, and in 60 years, it went to 40%, okay? So you can see, and natural gas in 1930 became 5%. So these are all new sources of energy, okay? And natural gas becomes 5% in 1930. And in 60 years, it has only gone to 25%. So as you can see, in 60 years, you get smaller and smaller percentage of energy consumption contributed by that new source of energy. Main thing it shows is that it takes a long time for a source of energy to become a sizable fraction. Now, currently, you can say, as we speak, modern renewables are about 5%. And if this trend holds in 60 years, which will be 2080, are we going to be even below 25%? Okay, so if this trend holds, I mean, that's what we are looking at. So the point is that this is exceedingly hard. This is happening even while 750 million people lack access to electricity. 2.6 billion people rely on biomass, coal, or kerosene for cooking, which is really bad for health of their children and their own health. Economic growth and rising living standards will require even more energy, as I showed you before. And energy is really a key to achieving sustainable development goals. So we want to achieve all this development across the world, especially in the developing and emerging nations, while controlling greenhouse gas emissions, which is the challenge that we face. So IEA has come up with International Energy Association, like many other bodies, global organizations have come up with scenarios whereby we can control greenhouse gas emissions from the energy system. And this is what they have come up with. So we are at 2020. Economic growth and population growth leads to 24% increase in the CO2 emissions. And then by 2030, through a series of mitigation measures like efficiency, electrification, wind and solar, and so on and so forth, we can knock this down by 50% and then get to net zero by 2050 by additional measures. So main point here is that solar, wind, and energy efficiency deliver about half the emissions to 2030, and carbon capture, utilization, hydrogen, etc., give the remaining reduction. There are many, many similar plans. I just picked this one because it's global and it's illustrative of what we need to do to bring global warming under control. And you can now put the Glasgow meeting in context that we are not on track to achieving this scenario. So what are the major strategies? Well, first of all, wherever possible, we need to increase efficiency, energy efficiency as well as materials efficiency, the way we are using materials and energy in our industrial and civil systems. Decarbonize the electricity sector. This is probably the path that is the most feasible given the technologies that we have in front of us. So generation using wind, solar, geothermal, and I include nuclear as a way to decarbonize the electricity sector. Then use electrification, sustainable fuels, hydrogen, etc., in the other sectors: transportation, building, heating and cooling, and industry and manufacturing. Finally, even with these, we are not going to get there. So we are going to need what are called negative emissions technologies, which is carbon capture, utilization and storage, nature-based solutions, etc. And I'll talk a little bit about all of these. So by now, I have probably depressed you that how are we going to actually do all this? So I want to now turn to some data and ideas that are signs of hope. And that's all that is. It's signs of hope and big challenges in front of us. So I think the most stunning thing that has happened in the last, say, 15 years is that PV solar and wind have been getting cheaper by the year. And now they are the most economical choice in lots and lots of parts of the world. So this is a chart that shows wind as being the most economical choice, onshore wind. You have PV solar being most economical choice. And so this reducing cost of PV solar and wind has been a dramatic change. And actually, it's really a beautiful story of how technological innovation and learning by doing, and that's actually a really nice empirical data behind this learning by doing, which leads to these kinds of cost reductions and increased utilization. So PV and wind are now compared with natural gas in the United States, and that just shows that the cheapest way of generating electricity, which is combined cycle natural gas, wind and solar are both very much competitive and cheaper in many, many areas. The other thing that has happened and is continuing to happen is battery storage is getting cheaper. So this is lithium-ion battery price outlook. We have gone from around $1,200 per kilowatt hour down to below 200. And the hope is we can get down to $62 per kilowatt hour. And what that's going to do is to drive electrification in transportation as well as integration of renewables into the electric grid. As a result of all this, power generating capacity additions have been largely wind and solar. And in fact, 83% of new capacity was renewable in 2020. So there's been just a dramatic increase in use of wind and solar in new capacity. Of course, there is a lot of existing capacity and there is growth. So both of these make these charts, while they are very, very encouraging and impressive, we have a long way to go. Now, a key challenge as we integrate more and more wind and solar into the grid is this engineering problem, which is really a problem of controlling the grid. And that's to ensure demand at any time t equals supply at time t. Both demand and supply, especially with wind and solar, are random variables. So at a high level of abstraction, the control problem that we face is how do we ensure that demand and supply equal each other pretty much moment by moment and manage the grid. So it leads to a huge field of study, which is design, operation, and control of electric grid in the face of inherent variability and uncertainty of wind and solar. There is a very large and complex control system that's evolving to make this possible. But it is possible, and many, many nations and areas are showing how to do this. This is to illustrate this variability that I talked about. So this is some data from the Tehachapi wind farm that shows production of wind energy from that farm on various days in June of 06. And you can see each color is a day. And what it shows is that there is no average day. So this is the average, but each day is so different from the average. To say that the average represents daily production, it just would be wrong. So this is to illustrate that wind and PV output depend, well, first of all, wind and PV output depend upon wind speed and solar irradiance, which are variable. And their power output varies at all time scales, even annual time scales, seasonal, winter versus summer, monthly, daily, hourly, sub-hourly. So this variability and randomness and uncertainty in wind and solar is a major issue as we want to have more and more renewables in our grid. Now, as we increase the amount of, say, solar into the grid, and if we are not able to manage the grid, so and I'm going to use the concept of flexibility to illustrate what happens. If the rest of the grid, which is other sources of generation, say nuclear, coal, natural gas, and demand, if they are not flexible, then there is too much solar at certain times of the day and too little at some other times of the day. So when you have too much, you really can't use it. So this chart shows that as you increase the amount of solar into the grid, you have to start curtailing it. You can't use it. And this shows the total curtailment, and the marginal curtailment can get quite high. So the economics of solar, which are so compelling, really are no longer compelling if we are not able to use that, and if you have to curtail this. So this, unless we increase grid flexibility, we are not going to be able to use all the wind and solar that we would like to use. So grid flexibility is a concept, and I'm not defining it quantitatively or rigorously, but the idea is, can the remaining generation and consumption stack be controlled and changed at will? And there are many sources of grid flexibility, and I've just listed some. So storage is the holy grail. If you can get storage at cost competitive prices and at scale, and you're going to need very, very different technologies to make it happen. So pumped hydro is the oldest form of storage, compressed air, batteries of various kinds, thermal storage, molten salt, hydrogen for long duration storage. These are all technologies that we are going to need and use them in controlling the grid. Second big source of flexibility is system operations. Like I told you, there is this very complicated and sophisticated control system that is used to manage and control the grid, which has forecasting, say, of renewables, forecasting of demand, scheduling and dispatching of generation sources. Those all system operations can be improved and optimized to increase grid flexibility. Market design. Electricity markets in many parts of the world are free markets or competitive markets, especially on the generation side. So this market design was done before renewables were such a big and important thing. So can we think about market design for renewable that is specifically designed for enabling renewable integration and storage, because renewables have this randomness and uncertainty attached to it. Another big source of flexibility is going to be transmission, which is like the hardest thing to build, but we absolutely need it because, say, wind is in certain geographical regions, but people live on the coasts. Solar is in, say, Southwest United States, and can we use that solar production to meet demand elsewhere? So transmission network would have to be expanded, and network management is going to be a big part of flexibility. And you can go further out into DC grids and so forth as enablers of grid flexibility. Load management. So far, we have treated load as essentially uncontrollable, but there is tremendous possibility through flexible loads, demand response, direct load control to harness the flexibility that's inherent in our demand for electricity. Flexible generation, combined cycle gas turbines with some carbon capture is a possibility, hydro is a possibility. And then finally, distributed energy resources, rooftop solar, storage, EVs, and microgrids on the distribution side can also give us grid flexibility. Each of these is a control problem that we can think about. Leaving beside the electricity sector, which I think is the one sector that I think we can do quite a lot, and we already have done, and I think we are on very much poised to make huge impacts in the electricity sector. I want to talk about transport and industry as well, because those are huge consumers of energy. So the IEEE net zero by 2050 talks about road transport, rail, aviation, infrastructure, and where we are and where we need to be. The main challenges in transport sector and main opportunities are, first of all, energy efficiency. Our cars, trucks, airplanes, they can all become more and more efficient users of energy. So that's certainly one big area, huge area. Second strategy or challenge is electrification. So EVs, they're taking off. And as we have more and more electric vehicles, what that does is it couples the transportation sector into the electricity sector. So we're going to get a huge increase in electricity demand if the EV approach to managing the transport sector becomes dominant, which is quite likely and possible given how the EV costs are coming down. So this is going to be another big opportunity in the energy system. And the third area is going to be sustainable fuels. That is, can we change the fuel from fossil fuel based to either synthetic hydrogen based fuels, where hydrogen is produced doing, say, renewable, say wind and solar, used to produce hydrogen, and then you use hydrogen to make fuels, or biofuels. And there is a lot of research going on in both of these. And in the transport sector, it's really, really important, as it is elsewhere, to account for the embodied energy, complete life cycle, because EVs, especially because of lithium, there is a tremendous impact on the environment. So unless you take into account complete life cycle and supply chains, you really don't get the decarbonization impact that you need. Another area, the area where we are really far, far, far behind is buildings, which are huge consumers of energy. And so essentially in buildings, the main approach is efficiency and electrification, and then some amount of hydrogen or bioenergy, and then behavior and avoided demand. That is changing the architecture, changing the way we use our buildings, and not requiring as much HVAC as we are used to. This is a huge problem, especially in the developing world, and especially if global heating continues. People will want to cool their buildings. So we are in for some really, really difficult challenge here. And I think from our point of view, building energy efficiency through modeling, sensing, and controls is a huge opportunity, as are heat pumps for building electrification. Third area is industry. Industry is another major source of carbon, of greenhouse gas emissions. And again, we are very, very far behind compared to the electric sector, where wind and solar are showing us the way. So here, what you have to remember is essentially this is steel, cement, other metals, and chemicals. And most of the CO2 emissions in this sector are going to happen in the emerging markets. And that's because lot of the manufacturing has moved to, say, China and other parts of the emerging world. So even though CO2 emissions are happening here, the consumption is happening all across the world. But the big issue is going to be, how do we decarbonize steel, cement, chemicals where they are being produced? So what are the approaches to decarbonizing in the energy sector? Again, energy efficiency is number one, material efficiency in production and recycling, material efficiency in products, fuel switching, use of renewables instead of, say, petroleum or other fossil fuel-based sources for manufacturing, process improvements and innovation, and finally, some amount of carbon capture and sequestration. That is, if you're going to use fossil fuels for this, then we need to capture the carbon. So it's a very, very hard problem. And we really are very far behind in terms of where we need to be. It is a really nice paper that has a conceptual view of decarbonization in the industry sector. And what it does is it starts with a product or a process, and then can we do more recycling? Do we need new raw materials? Do you keep an existing process or choose a new process? And then it sort of looks at the end game where the heat is going to come from. So basically, in all these industries, you have to think about where is the heat going to come from. So biofuels or hydrogen and synthetic methane, heat pumps. So these are all possible sources of heat. So for example, just as an example, if you want to think about industry sector, one area which is emerging now is hydrogen for low carbon steel manufacturing. But there is cement, there is other metals, there is chemicals. And here the opportunity is to do process design, modeling, sensing, and controls to enable these new industrial processes. As I mentioned, even if we make enormous progress on all these, we still don't get to net zero. So we are going to need some technology in maybe 2040 that can actually take carbon dioxide from air. And this gets to be the most speculative out there part of the thinking on climate change mitigation. And this is a very nice diagram that shows different ways in which we can take CO2 out. So there are nature-based solutions, and then there are engineered solutions. So for example, direct air capture, where you suck CO2 from the air, and to do it at scale and energy efficiency and cost competitiveness is like, we are just scratching the surface. Although, there are some demonstration plants that are out there. For example, in Iceland, there is a geothermal-based carbon capture demonstration plant. Now, that's just an example, but I think we are very, very early in this game. So far, I've talked about mitigation, that is how to avoid global warming, and we have to continue to do that. But it's clear that we also need to start working on adaptation and resilience, because already it is happening and it's affecting people and our societies as I speak. And one interesting thing about adaptation and resilience is that if you do it right, at least in some sectors, it can be synergistic with mitigation. So for example, microgrids, which are small scale grids with renewables, can give you resilience and independence from the power grid, at the same time allow you to decarbonize. Main topic it's a huge topic, that adaptation. So from our point of view, that is control and systems point of view, infrastructure resilience against large extreme events. For example, think storms, hurricanes, wildfires. If we can get resilience against these for electric power grids, for transportation networks, communication networks, then that can help us with adaptation and resilience. So just a little bit more on interdependent infrastructures. What is resilience goal? Is to minimize loss of infrastructure services. Think power supply to your house. Okay, you want to minimize the loss, the amount of time the power is down, and the extent of loss, that how many households are without power. So you can think about the loss of infrastructure service like electricity or transport or water during the event, so during a storm or a thunder or a hurricane, and then how long does it take to recover to say 95% of the service after the event. And so you can measure resilience, and there are infrastructures that we really want to make more resilient, and of course, electric power grid, our transport system, our water system, our communication system. Now, what turns out is that these infrastructures are interdependent. So just to illustrate electric grid, in the face of wildfires in California, for example, they do preemptive de-energization. That is, they cut off electricity supply to areas where the fire is going to be, so that the system doesn't go down, and when the wildfire is under control, they can energize the grid. You can do deployment of different energy resources. So rooftop solar and batteries, which are really important for mitigation, can also play a role in adaptation and resilience. That is, if you're out of the connection to the grid, you can still operate at some level in your house. Microgrids is another technology where, again, control plays a significant role for resilience. And then resilience through data integration, forecasting, and forward decision making. So let me show you a conceptual approach to electric grid resilience. So for example, let's say you know a hurricane is going to hit Florida or Texas. We know we can predict this hurricane event, say 5 days ahead, or we know it's coming. We don't know exactly where it is coming, but we know it's coming. We can forecast a system level path. As new data comes in, we can improve the forecasted path, and data streams from various kinds of sensors and observations, meteorological observations, and so forth, can improve the prediction. And as new data comes in, we can improve the forecasted system path. And then you can improve your plan, because one of the major approaches to, say, dealing with hurricanes is, where do you position transformers, etc., in the city or in the region, so that when the hurricane is gone, you can replace, say, damaged transformers. So you have to position the crews and the materials ahead of time. Can you make a really optimal decision on this kind of positioning while you are improving your system path? So it's kind of a feed forward decision-making problem, which you improve your decision as your forecast improves. So it's a very interesting resilience question, where you can use techniques from our field of decision and control and forecasting. Sort of the main point I want to bring home in the rest of the talk is climate change mitigation adaptation. There is just pervasive opportunity for our field. So this is the only slide where I'm going to show what I have been doing with my colleagues and collaborators and my students. So a bunch of areas where we have been working: renewable producers and storage in electricity markets and operations; strip packing, which is a computer science technique for peak load minimization; causation-based cost allocation principles. You get into a little bit more economics and game theory; distributed control for integration of renewable resources; matching markets for distributed energy resources; stochastic optimization for residential grid management. So lots of stochastic control, optimization, modeling, game theory type of techniques, and then cybersecurity and smart grid. So you can go and look up my papers and presentations if you are interested. First sort of observation: in this area, it's systems everywhere. Everywhere you look, there are systems. Systems are ubiquitous, whether it's at the level of, say, a wind farm, a wind turbine, to the electric grid. And you can say the same thing about industry and transport. Everywhere you have systems and interacting systems. And they're multi-scale. The grid goes from milliseconds, microseconds, all the way to annual cycles. So they're multi-scale in space, in time, in organizational boundaries, say utilities versus state versus generation companies versus consumption companies, and regulatory. So how these various energy sectors are regulated plays a big role in the energy system. There is ubiquitous need for systems-oriented problem conceptualization and formulation. I think we have a really interesting background to take a systems view, because all these are systems problems. Huge opportunity for architectures, both information architecture, physical architecture, and organizational architectures. modeling and simulation everywhere, sensing, monitoring, estimation, prediction, ubiquitous opportunity for these types of techniques, control, co-design in particular, designing of control and the system at the same time, and then decision and control algorithms, distributed, stochastic, nonlinear, robust, game theoretic learning. So all these techniques are usable. One point I want to sort of bring home is, especially for infrastructures, and energy systems are infrastructures, they have long life cycles. So a grid or a transport network, is going to be here for 60, 70, 80 years. We really don't know what the world will look like in 60, 70 years, but our decisions today affect what that is going to be. So how do you make decisions, important, say, capital allocation decisions, with so much uncertainty out there? So there is an emerging field, which I think is just absolutely fascinating. It's not quantitative yet, although it's getting there, is decision making under this kind of deep uncertainty. Second point I want to make is transdisciplinary collaboration is going to be absolutely essential. Control alone is not going to solve any of these problems. So we need domain experts from engineering, controls, physical sciences, computing, social behavioral sciences, and even humanities come together along with end users and communities, because you really have to situate research in the communities where the work is going to get used to conceptualize, formulate, and solve these problems. Systems and control experts should and could become members of such teams, and we could possibly even lead such teams if the opportunity arises. And here I want to point to the emerging convergence research paradigm that when I was at NSF, we really pushed very hard on, and it's a really good way to go about doing this kind of transdisciplinary work. Third point I want to make is, research alone is not enough. We have to connect it to technological transitions, because energy system solutions must scale. I showed you the gigantic scale of energy systems. So if our technologies and solutions don't have this kind of impact at scale, and so say for the US, I mean, one way to think is, does it affect 1/4 of energy consumption? Well, if it does, then there is a chance that we are going to make a difference. And the point is, it's possible. So the PV, solar, wind, and storage are inspirational success stories that, yes, we can do things at scale, but it requires the kind of collaboration that I mentioned. Research needs to be connected to real-world innovation at relatively rapid time scale. Why? Because time is of the essence. We are looking at 2030 goals, 2050 goals. Additional comments: technological innovations have a combinatorial character. There's essentially, we combine different technologies to enable an innovation. So again, we have to think about what we do, say, in controls, working with other types of technologies to bring together solutions. There is a really wonderful work going on evolutionary reconfiguration in systems change and technological transitions, because that's what we are looking at. And then deepening understanding of how research and technological innovation systems progress. So this goes to issues of architecture and research formulation. The final point I want to make is that really we need to think beyond science and engineering research. So this is not just an engineering or science problem. I already have mentioned use of, collaborate with social science and humanities, but it really is ultimately about humans and communities and societies. We have to be very mindful in this space of social justice, generational equity, and global nature of the problems. If a solution doesn't work for developing world, chances are it's really not going to solve the problem. So we have to think in those terms. We have to think about those who are going to be hurt by climate change. Are the solutions taking into account social justice? Huge problems, but we need to bring them to the table in problem formulation and conceptualization. My great hope is our students. Students are very, very interested in these problems. So even though you may not work on climate change mitigation and adaptation types of issues, you may be working in different fields. Many of us are educators, and we have a critical role as educators to bring examples from this field into what we teach, just so that our students who are hungry to work in this area can be exposed to how we can engage with these topics. And finally, I think we need new narratives for the future of human civilization, so we can go from the track that we are on to a more sustainable future for our children and our grandchildren. I want to conclude the talk by talking about an effort that Anu is leading along with George Papas and Kaya Johansson on Control for Societal Challenges, Roadmap 2030. Tariq Samad and I are co-leading a team on control for climate change mitigation adaptation. And we have assembled a very nice group of people from our community to think about it. And there is a warm and open invitation to anybody who's listening to join this effort. With that, I thank you very much. Thank you, Anu. Thank you, Magnus.